Dr.M.G.R Educational and Research Institute, University, Madurai, Chennai.
Durga ma'am.
Ma'am, shall I start?
Yes, ma'am.
Yes. Good afternoon. This is Dr. Durga Subramani, Assistant Professor of Chemistry. On behalf of Dr.M.G.R Educational and Research Institute, we are extremely glad to welcome all the eminent personalities, heads of various departments, staff, students, and today's participants to a one-day national level webinar on third harmonic generation of inorganic compounds, organized by Department of Chemistry, Faculty of Humanities and Science, Adayalampattu Phase II campus. To present on this topic, we having with us today's chief guest, Dr.D.Anbuselvi, Assistant Professor, Muthayammal Engineering College, Namakkal. Inorganic chemistry is becoming more and more interdisciplinary, providing innovative uses and approaches for ancient metal elements that can find new life in various applications. Currently, the antimicrobial and antifungal activity of silver is exploited in a very miscellaneous set of applications ranging from simple consumer goods to complex medical devices. Here, inorganic compounds can indeed have an impact on the quality of life and also the well-being of the increasing population of the world. It's really challenging conducting an appropriate program in this pandemic situation. Our university is excelling in conducting events in an elegant way, even in pandemic situation as well. I take this opportunity to express my sincere gratitude to our M.G.R University for tirelessly servicing the society with high-end techniques, moral values, social responsibilities, and compassionate about underprivileged people. I really feel very proud to being a part of this institution. At this point, I would like to state Tamil quote here, I feel which exactly suits to our management. Anna Sattiram Ayiram Vaital, Alayam Padinayiram Natal, Pinnarulla Darumangal Yavum, Payar Vilangi Olira Nirithal, Annavayinum Punniyam Kodi, Angor ஏழைக்கு எழுத்தறிவித்தல் எனும் பாரதியாரின் கவிதை கிணங்க ஒருவருக்கு அழியாத செல்வம் கல்விதான் என்பதை புரிந்து கொண்டு அத்தகைய உயர்ந்த செல்வத்தை அனைவருக்கும் வழங்க வேண்டும் என்பதற்காக பொறியியலிலிருந்து அறிவியல் வரை அனைவரும் அத்தனை துறைகளையும் நிறுவி ஏற்படுத்தி பல்வேறு மாணவர்கள் பயன்பெறும் வகையில் பல கல்வி நிறுவனங்களை நிறுவி மிகச்சிறந்த கல்வி சேவை ஆற்றிக் கொண்டிருக்கும் எம் பல்கலைக்கழக துணைவேந்தரும் நிறுவனருமான உயர் திரு ஏ.சி. சண்முகம் ஐயா அவர்களையும் மேலும் அவர் வழி நின்று நடத்தும் உயர் திரு எம் பல்கலைக்கழக தலைவர் உயர் திரு ஏசிஎஸ் அருண்குமார் ஐயா பொறியாளர் அவர்களையும் இந்நேரத்தில் நினைவு கூறுவதில் பெருமகிழ்ச்சி அடைகிறேன். With this quote, I would like to invite Dr. Nirmala Krishnan, Professor of Chemistry, for welcome address. Ma'am.
Can you hear me? Am I audible, ma'am?
Yes, ma'am, you are audible. You can proceed now.
Thank you. A very warm good afternoon to everyone present here. Learning with cooperation, positive attitude, and mutual respect are part of everything we do and say. With a small message, myself, Dr. Nirmala Krishnan, Professor, Department of Chemistry, feel extremely privileged to deliver this welcome address. On the occasion of one-day national webinar on the topic, third harmonic generation of inorganic compounds. First and foremost, I would like to extend my sincere and hearty welcome to our Honorable Founder Chancellor and our Honorable President, who always supports and encourages to conduct such events. I feel extremely happy to welcome our Vice Chancellor, Ma'am, Registrar, Director, Sir, Additional Registrars, Joint Registrars, Directors, and all the executives of Dr.M.G.R Educational and Research Institute, University. I extend a warm welcome to all the Dean, Deputy Deans, Head of the Departments of various faculty, all the teaching and non-teaching staff of various faculty, and wonderful participants of today's event. I extend a warm welcome to our Dean Academics, Dr. Arunachalam Sir, and Dean Admin, Dr. Sindhil Kumar Sir of Phase II campus. My heartiest welcome to our distinguished guest speaker of today, Dr.D.Anbuselvi, Assistant Professor, Muthayammal Engineering College, Namakkal. Today she is with us to discuss on this topic, third harmonic generation of inorganic compounds. We are ready to hear, ma'am, and a heartiest welcome to you, ma'am. And once again, I welcome all of you for this webinar. Thank you. Over to Durga, ma'am.
Thank you, ma'am. Next, may I please request respected Dean Academics, Dr. A.R. Arunachalam, for felicitation address. Sir. So, you're not audible, sir. Please make sure your mic is unmuted. No, sir, you're not audible. Yes, sir. Yes. Now it's audible.
Yeah. Thanks, ma'am. Sorry.
Yes.
Yeah. Sorry. So, on behalf of Dr.M.G.R Education Research Institute, Adayalampattu Phase II campus, I would like to welcome you all to this one-day national webinar conducted by Department of Chemistry on the topic third harmonic generation of inorganic compounds. To start with, I would like to thank our Honorable President, Engineer A.C.S. Arunkumar Sir, for his constant support and motivation towards conducting a lot of activities. And I really thank him for his kind approval today to conduct this wonderful national level webinar. So next, I would like to congratulate the Department of Chemistry for the constant effort shown towards conducting a lot of activities through online mode. To start with, I would like to congratulate the head of the Department of Chemistry, Dr. S. Valliyamma ma'am, along with other the team of faculty members who are successfully coordinating and organizing this one-day national webinar. Dr. Nirmala Krishnan ma'am, Dr. Rama Priya ma'am, and Dr. Durga ma'am, and Ms. Aparna. So I really appreciate all the entire faculty members who have involved themselves in successfully organizing this national level webinar. So next, I would like to welcome the resource person for today's session. So resource person are always very important for a session. So I really, on behalf of Dr. M.G.R Education Research Institute, I would like to welcome the resource person for today's session, Dr.D.Anbuselvi ma'am, who is assistant professor at Muthayammal Engineering College, Namakkal. So thank you so much, ma'am, for spending your valuable time with us, sharing your knowledge with n number of participants who are watching this event live. So really appreciate all the participants also for showing your interest, registering for such kind of very valuable, knowledgeable sessions, attending these kind of sessions. So definitely, these attending these kind of sessions will definitely enhance your knowledge, add more value to your professional career as well. So really, on behalf of Dr.M.G.R Educational Research Institute, I once again welcome the speaker for today's session, and also I welcome all the participants, especially for spending your time and watching this event live. So I wish this event a grand success and wish the department all the best. And I also thank the department for inviting me to talk a few words about this particular event. So thank you all. Have a great session and have a great day too. Thank you all.
Thank you, sir. Thank you so much. And this is a time for the introduction of today's chief guest. Let me call upon Dr. L. Ramapriya, Assistant Professor of Chemistry, for the introduction of chief guest. Ma'am. I'm sorry, again, check your mic. There is some problem because it's not audible.
Is it okay now?
Yeah, now it's okay, ma'am. You can proceed now.
Yeah, fine. Thank you, ma'am. Good evening to one and all present in this gathering. I'm very delighted to introduce today's speaker. Dr. Anbuselvi started her graduation as BSc Physics in 2008. She completed in Tiruvallur University. She completed her MSc Physics in 2010 and was awarded as a university rank holder. With MPhil Physics in University of Madras at 2011, she continued her research in Laila College, University of Madras, and was awarded PhD in 2015. With her professional experience, she started as assistant professor in Central University, Pondicherry, in 2016. She continued her service as assistant professor and head at Adayalampattu College for Women, Viluppuram. Presently, she is assistant professor at Muthayammal Engineering College. She has submitted and working on various projects, funding projects. Currently, she is also a reviewer of various journals. She is also she's a reviewer of Material Research Innovation, Taylor and Francis Journal. She's been awarded as a Certificate of Reviewing Award for a few of the journals like Physica B, Physics of Condensed Matter, Materials Today Proceedings, and Journal of Physics and Chemistry of Solids. She has many publications to her credits. She has attended many seminars and conferences. And she is also expert in many of the online courses and conducted many courses in the online. With a lot of her very good profile, I'm very happy to invite her and give her speech. Please, ma'am, you're welcome. Ma'am, you are not audible. Your mic is muted.
Now it is, ma'am?
Yes, go ahead, ma'am. Yes, ma'am. Go ahead, ma'am.
So, very good afternoon to all. So first of all, I'd like to thank to this organizing committee and the management for this invited talk, and special thank to this Madam introduction to this Madam Priya ma'am. So my presentation is mainly focused onto this third harmonic generation. Just I want to share with this PPT. Shall I share this, ma'am?
Yes, ma'am. You can, ma'am.
Yes. So, ma'am, is the PPT visible, ma'am? Ramapriya, ma'am?
Ma'am, please go to the Slideshare mode and share it, ma'am.
Ma'am, is it visible?
Yes, ma'am.
Okay,
Yes,
okay,
ma'am.
okay.
You can go ahead, ma'am.
Okay, okay, ma'am. Thank you. So my presentation is completely focused onto this third order nonlinear optics. So what does mean by the, so I have to give this harmonic generation. So it is very simple. So it is a nonlinear optical process. So in which n number of these photons with the same frequency, it will be interacted with this nonlinear material and generate a new photon. This is called by this generally given harmonic generation. So we have to explain to this third harmonic generation is. So we'll go for this slide. So this is my outline of the presentation. So nonlinear optics, analog materials. So third harmonic generation using the Z-scan techniques. So optical switching applications. So first is just I want to know this known things to the unknown thing. So that known thing is the linear optics, right? So linear optics. So what is meant by the linear? That is you know very well. So just I will explain about what is the varying from this linear to the non-linear optics. So in linear optics, the properties like an refractions, polarization, etc. So these are the things it can be observed through the weak light. So weak light, which means that low intensity light, right? But in this case of this nonlinear optics, the properties of the materials depends on the intensity of the light, which means to this high intensity laser light we can use it that. So it means nonlinear optics won't happen in the weak light. So that is the main difference of it. So it is needed to the high intensity to change the material properties. So that's why we have to move on to this particular third harmonic generation. So for the second point, we have to note this here. Superposition principles hold the good in the weak light then compared to the intense light. So comparing to this intense light, so it will be an weak light will be an superposition principle will be good. So this third point, this is a very important one. So the third point is we can represent as the refractive index and absorption of the materials are independent of the weak light, which means the linear optics. But in this case of the non-linear optics, so absorption, so we have to here discuss only for this particular two parameters, that is the absorption and the refractive index. Okay. So the non-linear optics, absorption and refractive index mainly depend on the intense light. So that is why we are mentioning it as non-linear refractive index and non-linear absorption. So this particular two things, two parameters we are going to calculate for the third harmonic generation of this particular material. Which material we have to use it, that particular material we can calculate. Okay. So it means the refractive index and this absorption of this material are not say constant. So here it is I given this noted down. So refractive index and the absorption of this material are not constants when the high intense light is passing through the materials. So it will be changing to this based on to this intense light. We will see that what will be happen, what are the values will be changed in some different material like organic, inorganic. So what is the semi-organic materials? What are the things will be happen? And we'll see in the future slide. And so the last one is that will be an interacted in high intensity. You can control the light with the other light in this non-linear medium, but not possible in the. So here it is not possible for this particular linear medium. So this is we have to know the difference between to this. What is mean by linear? What is mean by the non-linear optics? Okay, so I hope you have to understood what is the linear and non-linear. And we'll see the next slide. So in this slide we can see that two kind of this laser light. So one is the red laser light and another one is the green laser light, right? So in the general we can produce the red color laser light is an direct way or an easiest way we can, as well as we have to purchase in the market will be an very easiest way. But in the case of the green light, it is not product is not directly make it for the manufacturer. So why it is not possible is then how they are manufactured with the screen laser. So we have to raise one question. So they will see the next slide. I'll show the what is the manufacturing process inside the particular green laser. So this is the inside that our power point, right? Laser point. So in this particular red color laser point we are using in that presentation, in that our smart classroom we are using in the presentation skills, right? So here it is the, so green laser is the, here just I have to point it out, only important point is the KTP or an York crystal. Says in this particular setup we are using for this KTP or the York crystal. So what is we have to purpose to using this particular material in that setup. So it is an, so one thing is, first thing is a, so the KTP is the nonlinear optical crystal. So this is in second harmonic generation process. So what will be happen when the second harmonic generation process is, it is converting the, so particular wavelength, that is 1064 nanometer to 532 nanometers. So I hope this values you should know the which color is the 532 nanometers exhibiting to the 532 nanometers. The white color light will be converted into the so green light process. So this is the very important of this purpose of this particular nonlinear optics. So third harmonic generation is also a nonlinear optical process. So this is a very important thing for an KTP, and this, that is the full explanation of this KTP is given here. And this generally we are in our daily life. So in what kind of this way we have to use the nanolo material is, here I can given the different field or different areas I have to given. So what are the applications we are to using to this nonlinear optical materials. For the nucleus, suppose we have to generate it for this using through this material, particular nonlinear material. So we have to make it for a, one thing is when a new color we can produce for this. And second one is a control to this particular frequency. Control to the frequency means some of this program they are organizing to the some of this outside of this program. They are using to the different colors in the particular breakage of this frequency, right? So that blue color and red and to the green, some of these many colors they are using, right? So that particular colors we have to differentiate it. They have to break. We can break and control to the particular wavelength and to the pulsing process. These are to the diversifying lasers and to the light. So what we have to the material interaction is, so machining and to the analysis tools and for the spectroscopy purpose. And in the field of ID, that is information technology purpose, so telecom and to the sensor. So generally most of the students who should know the sensing of this, you are sensing to this your ID card when you are entering to this college. We are sensing to this, you are recording to our ID number. So that will be as recorded to this. So using to this particular sensing of this laser. So by the biometric apps also, we are using to the sensing of this, some biometric system we are using for this for our faculties. So that particular usages we are using for this particular nonlinear optical material and data storage and then signal processing. So what is the effect of this linear effect? So you have to see this. So it's in the normal linear optics. You just consider for this input wave is a normal linear optics. So light waves act on a, just consider as any kind of this molecule we have to consider. So when you apply for this input waves, so into this particular molecules, we can get the emitted waves also as a, what it is we have to use it for the input wave, that is also we can get for the same light, that is original light, we have to get it for the same original light. So here we have to denote it as a, so energy level diagram also given here. So that is the input light photon energy, that again to this emitted light is the photon of the same frequency. So that we can also imagine this process in terms of this molecular energy levels. So using to this particular arrow mark is given, right? So using to this arrow mark, we have to denote it. So what is in the case of the nonlinear is, so now we have to apply, suppose the irradiation of the high enough. So let us consider same molecule, any kind of this molecules. We have to differentiate the So input wavelength I have to given here. So that input wavelengths we have to, first thing is, one thing is the emitted output wavelength waves is a emitted wave is changing to the, one thing is new color. So another thing is it is a double the frequency. So frequency will be double the half of the wavelength will be half of, right? So here it is that is given here. So that a high frequency, the high energy state it will going on. So let us consider. So if it is this, then ground state, and it will move on to the second level of the state, again to this excited state, and return back to this to the ground state. It will be emitted of this some of this energy, that is the H2 H nu of this energy will be and produced in that. So in that second harmonic generation is already we said that nonlinear optical process that result in the conversion of the input optical wave so into the output wave is twice the input frequency. What do we have to apply for this input wave? So it will give it to this twice the input frequency. But then we have to go for a calculation for this wavelength, that is the of the wavelength. This is because it is inversely proportional frequency and the wavelength. So that is an of the wavelength. So frequency will be an double. So next we have to see the, so what is the process inside that? So this is the site is the representation of the second order. So omega, that is frequency we have to apply for this particular material. So we can get for that 2 omega, that is the output. So that polarization is so directly proportional to this electric field. So the polarization we can denote here. So it's directly proportional to the electric field. So linear, so this one is the psi 1 is the linear susceptibility, and energy level just now we had to previous slide also explained. So the energy level is the 2 for this so set that for energy level 1, and move on to this exciter, again back to the ground state. This epsilon naught is the commutative of free space. Again we have to move on to the, so epsilon naught psi power 3 and EQ. So this process is for the third harmonic. Next we will be given for the third harmonic also. So similarly in third harmonic generation, this is our title of this purpose. So similarly in third harmonic generations, so molecule absorbs photons and move to the third excited level. So during to this excitations, the excitation of these molecules emit the fundamental frequency with 3 times of applied angular frequency. So that is a very important of the purpose of it, right? So how we can say for the energy level is E equal to H nu. So the response of the output frequency 3 omega, that is created by an applied field of the frequency, it is a so omega, right? So this is it. So how they are to going to the purpose and then process in the inside that. This is a very important process. So polarization, here it is a polarization is directly proportional to this electric field, right? So which means the polarizability. So when we can see for this in the microscope view, what is the process inside is we happen. So in general, so the molecule that have an the dipole moment. So for an as a chemistry or any people science people know that. So have a dipole moments, that is that kind of the charges. So that particular dipole moment so oriented in that particular electric field. So that particular orientation will be happen inside that. This is we had just said that nonlinear second order nonlinear optical material. So here it is force will be acting on this. That particular force is that is on the system in a, so that particular target that is related to the angle between to the dipole and to the dipole and to this electric field. So you know very well the dipole is a vector quantity. So which means vector is a one thing is magnitude and the direction is there. That is the thing. So dipole is having the magnitude and direction. So in opposite field will induce a dipole. So in that opposite direction. So this is an opposite field induced into this opposite charge direction. So when you apply electric field, if you plot between, suppose if this process is happen, and they plot between to this electric field and to the say induced polarizations, the slope of this line of this function of the linear polarizability. So how much is the ability to polarize a particular material is the value of this alpha, so which means a greater amount of polarization for the same amount of the applied field. So we use the dipole moment. So is equal to the alpha is a linear polarizability and with respect to the field. This is will be happen. So but in this is a non-linear. So what will be happen? So for the polarization process, what is the happen in this linear and to this non-linear is first thing is I will expand about to this linear polarization. How they polarize to this light. So first thing is when we use it for the light source in this linear polarization, light source, any light of the source, normal light source. So light wave vibrate in any direction. So when you go for a light spread it out to the any direction. See this. So all the directions. This particular direction you have to polarize to the single direction. So we have to use it for the polarizing filter. One thing is here use it for. So that particular polar using to this polarizing filter, again we have to polarize one single direction of this polarization, right? So this is for and we have to get the apply for this input, that is a light source. We can polarize for a using to this polarizing filter. Same thing will be what is happening is a non-linear polarization. Same polarization is will be happen, but the getting to this output is so it's totally rotating to this particular plane. So the output is we can know the difference. You can see the difference, right? We can get the output as frequency shifted photon. So how much of the photon is incidence? We can different for this. We can get this output is so different frequency. So here it is. We can feel the difference of this coloring of this presentation, right? So that corresponding to this dielectric medium or to the polarization is an electric field. So it is then diverge to this particular what is the direction is to change into the direction. And the next is so this is then to this response of this, including to this equation is given for this is V is equal to epsilon naught psi 1 E plus epsilon naught psi 2. So E square plus epsilon naught psi 3 E cube. So this is the polarization directly proportional field, right? So this is for an we have to focus for that particular third order harmonic generation. So induced polarization of the mediums, epsilon is the dielectric constant of the vacuum, and so is the electric field, psi is the constant. So here it is the separately what is the non-linear polarization. So this particular part is we denoted as a permanent polarization, and second one is the first order polarization, and second is the second order polarization. We have to take it out the same equations, and third order is the so E cube of this side, right? Yes. So coming to this point, so absorption, and to this we have to find out to this one thing about absorption and refractive index. So now we have to see for this absorption. So this material of the linear and non-linear material. So see this diagram for this linear absorption. So here it is this is in ground state. When a energy we can give for a h nu energy we have to apply for this particular material. Then it will go for an excited state. Again back to this same energy will be produced, that is the h nu of this energy we can emitted. This in this particular process of linear absorption. And this non-linear absorption process here to this so ground state and to the go for the so existing of this photon and go for the electronics excited state. So and then virtual relaxation stages here, and then emission of this photon of this, that is the we can go for the energy level. Finally, we can go for get it the h nu of this 3 times of this, so energy level. So here it is one important thing is alpha equal to, so nonlinear absorption, so coefficient equal to, so alpha naught and plus beta I. So alpha naught is the linear absorption and so beta is the nonlinear absorptions. So this is we have to find out. So that is we'll discuss in later. So that is it. I is there based on to the depends on the intensity, the absorption, nonlinear absorption change already we said in the first slide. So nonlinear absorption. So nonlinear absorption is the change in transmission of the material. So as a function of intensity. So this phenomena is manifested optically. Yeah? So two things happen. Any kind of this material, just I am telling you commonly. So any kind of this materials, the absorption, nonlinear absorption is there. So optically, one is a reduced. So that is we can using to this word in this third harmonic generation saturable, right? So or increase the absorption. One is the reduce to this absorption, or another one is the increase to this absorption. So that is the we can increasing to this absorption process. We can say that reversible saturation. So these two things only will be happen. So one organic or inorganic, any kind of the material. So based on this particular calculated value, we have to set that this is the reduced or is increased absorption, right? So what is the, so this particularly, so non-linear absorption, right? So this particular non-linear absorptions is directly proportional to this imaginary of this susceptibility of the 3, that is third order susceptibility of this particular material. So if it is that particular absorption will be increases, the imaginary part of the susceptibility also same way. So that is the both are in a directly proportional. So what is the mechanism will be possible for this particular N elements nonlinear absorption? So in this process, optical absorption process occur when materials are eliminated by a strong laser source. So nonlinear absorption is the proportional to this square of this intensity. So nonlinear absorptions is directly proportional, that is the I square. So how it will be mechanism will be happen. So slowly they will go for an first one thing is the one photon absorption. Again this is the this mechanism is the 2 photon absorption. We can visualize to this energy levels also. This is the third photon absorption. So this is a process for non-linear absorption for so third harmonic, and to the 2 photons absorption what will be happen, then only we can understand for the 3 photon absorption. So in the 2 photon absorption, so generally we said TBA or the 2 photon excitation we said that. So this particular, so TPA, that is 2 photon absorption is, so simultaneous absorption of 2 photons is an identical or a different frequency in order to excite this particular molecule from one state to the higher energy state. So that particular TPA, that is 2 photon absorption is directly proportional to the I square. So here I have to given one equation di by dz, that is the change in the intensity is equal to alpha I minus, that is beta I square. Here it is the alpha is the absorption coefficient and beta is the 2 photon absorption coefficient. So I square is the radiance, the intensity is the square of this part. Here one figure is given here, right? So this figure, so it is denoted as one. This is an 1 photon excitation, right? So from this we can see that, so that particular inside to this coming to this waves will be n spreaded to this, but full space will be n occupy of it. But in the case of the 2 photon excitation, we can get this precise to this particular waves. We can get that. So what is the? I think you see the conventional waves. So this Rayleigh length, so you can say that Z is we have to denoted here. So that is the Rayleigh length. So Rayleigh length. So in this basic classes we studied about to this Rayleigh length. So that is the related parameter in this confocal. So let is taken for this particular angle and to this parameter. So it is the, so we can take from this Rayleigh length is Z. So this particularly important when beams are modeled to this Gaussian beam. So please noted the word of this Gaussian. So this is used into this instrumentation purpose. So this process will be happen in that particular instrumentation process. That's why I am given here. So this is the depends the Z is so Rayleigh length. So this is the mechanism that shows state and excited state for the two photon absorption. Again, for the similarly, for the this is self, so two beam and to the three beam. So here we have to use the square of this intensity we said in the second two photon absorption. So the three photon absorption, so alpha I and this gamma is the three photon absorption coefficient and the I3 is the intensity is the radiance, right? So it's an, so now we can see this. So this one is the when spread out and that is diffractor, that single line is not appeared properly. It will be an diffractor from here to here, and we can get in here it is a one spot light, right? So what is the difference? So this one is the excitation by one photon result in absorption along the entire path of the laser beam in the curve. So this is a single, here it is, see this. So the one photon absorption of this output is, see we can get this like this. But this, in the case of this two photon absorption is confined this particular volume very close to focus where the intensity highest, giving rise to the pinpoint of the 3D circulation. So this is the precise and to this spotlight and then very accurate to this light. So this is the purpose, this is the usage of the second two photon absorption. So this is a two photon absorption is directly proportional to, already we know very well. So that is the square of the intensity. So that is I equal to Z power, that is 1 by Z square. So that I already said that what is meant by Z. So that is high intensity is directly proportional to the 1 by Z square. So this value you have to substitute to this equation and we can get to this two photon absorption is directly proportional to the Z power minus 4. And to this, what is the diffraction will be in linear and non-linear optics. So the refraction of this linear refraction is the, so that is will be very general already we will discussed. So in this non-linear absorptions, this composite is just to change in the direction. So refraction is change into the normal direction, a third change in the direction. So this is for the glass slab with the different refractive index. So N1, N2, this is for an example purpose. And this is a N of I, so that is important. N of I equal to N0 plus N2I. So N is the refractive index, depends on the intensity. So N0 is the linear refractive index. So this was calculated in the U visible NIR. And to this, N2 is the nonlinear refractive index with respect to this intensity, right? And to this is the third order susceptibility of this figures explanations. So the imaginary and the real. So susceptibility psi 3 we can add it to this imaginary and to this as a real. So imaginary for this linear and to the non-linear process, that is one photon and the two photon absorption. I will be appearing to this graph. This is I have to given here. And this is the yes. We are waiting for this particular instrumentation purpose. So this is the method is the Z-scan techniques. So using this particular technique, so we can calculate the third harmonic generation. So how they are instrumentation is to be operated. That is, suppose if you So I will ask you to this organizing members to play any videos. Otherwise, I will explain. Rama Priya ma'am, is it possible, ma'am? Rama Priya ma'am.
Hello, yes, ma'am.
Ma'am, is it possible for a
Hello,
video? Otherwise, I will explain it. No problem, ma'am.
ma'am. It's better you can explain it, ma'am, than
Yeah.
playing the video.
Okay, ma'am. Okay, ma'am. No problem.
Yeah, please, ma'am.
Okay.
Yes, ma'am.
Okay, thank you. So that particular here, just let us consider. So is the one thing, two kind of the laser we are using particular systems that scan. So helium neon laser and another one is the ND laser. So here it is the we are using for the helium neon laser. So here I hope just to move on to this slide so we can understand very well. So this is a laser, right? So this is we can get the very clear view. So this is the laser. So when you input wave, that is the that wavelength is the 633 nanometer that laser is in. So when you apply for this Gaussian filter, so already we said that what is the here I explained what is it. Yes. So this is in this particular region I'll explain what will be the Gaussian filter will be did that this particular process will be happen for the using to the Gaussian filter that will be converted to this particular wave. So, so this is all happen in this particular region Gaussian filter, and then using to this aperture one 2 mm size aperture as we use it, and to the one lenses we have used it for to convert the sample. Here we have to place it and hold it to the sample. So the sample, so we have to should be an less than 1 mm. So two kind of the sample we have to use. One is the solid or another one is the liquid. So the powder form, if you want to use into the powder form, so that we have to bell it out and then we can use. So this is the process here itself we are going on. One is the solid and liquid. So that particular sample we can take the size of the less than 1 mm we can take. Again that particular rays will be reflected to this particular lens, and again you can get for this one aperture. That aperture is the variable aperture. So here we have to use it for the convex lens. It's an adjustable, so aperture is used for the closed aperture. So two kind of the process we have to make. One is the open aperture, another one is closed aperture. So for this open aperture, we have to remove for this particular aperture. Again, to the for the closed aperture, we have to insert to this particular aperture. So two kind of the parameter we have to calculate. So what is the parameters? We'll discuss on the next slide. This recorded value you have to sensor using to the sensor. Again, we can get this value in this this database using to this particular system, and is so this is for an important thing. Third order susceptibility. So third order susceptibility is that is the one is two kind of things. So nonlinear refractive index and nonlinear absorption. So nonlinear refractive index, that is N2, so is directly proportional to the real of psi 3. So two things is the real and imaginary part of this psi 3. So the real is the directly proportional to this refractive index. So here the students are did this refractive index calculated in the spectrum using to the spectrometer in our school days, or to the first years or second years also they are using to the refractive index of the prism or refractive index of the solid prism, something is it, right? So here what will be the happen, the values will be comes for this particular material. You see the next slide. So the concept is real is directly proportional to this nonlinear refractive index, and imaginary is directly proportional to this nonlinear absorptions. So it's in this experimental measurement of N2 and beta are allowed to determine the real and imaginary part of the third order nonlinear optical susceptibility. So this is the third order susceptibility of the psi 3 is considered as a complex quantity, and it is defined as the, so this is a formula, main formula. So when you go for the calculation, what I want to calculate for the third harmonic generation calculation is here. From here itself we can start. So psi 3 is equal to real of the psi 3 square plus imaginary of psi 3 square, that is the square root 1 by 2, right? So again we'll see what is real, what is imaginary. Again that is also inside that what is the, again to the n2 and beta. The experiment measurement of n2 and beta are allowed to determine the real and imaginary part of the third order non-linear optical susceptibility psi 3. So the real of psi 3 is equal to this Z unit. So is equal to this 10 power minus 4 epsilon naught n naught square c square. So by so pi. So the n2 is the very important. So that is the absorption. So the refractive index. So here it is symbol also, please note it down. So symbol is the refractive index. This is the absorption is beta. So here it is multiplied by the factor of n2 is the refractive index, and imaginary of the psi 3 is the 10 power minus 2 epsilon naught n naught square c square lambda by 4 pi square into beta. So this is the, here it is n naught is the linear refractive index, and this is already known nonlinear refractive index. This beta is the nonlinear absorption. So this particular calculation I'll explain in the next. Is closed aperture. Two things is there: closed aperture and open aperture. So say example we have to place it here, and then lens is left as the lens. For the aperture we have to closed aperture. We have to sit at the aperture. Just we will move on to the sample front and back. This particular is this direction. And then we can deduct for this particular samples of this materials isn't harmonic, and to the detector value. So the detector values parameter you have to drawn it as a graph. So see this graph. So the graph here is the peak, this is the peak, this is value. So this particular peak value of the difference is the transmittance, that is the difference between the change in transmittance. So if it is the transmittance is increases, so the the transmittance is decreases, so automatically the refractive index is so increases. So here it is the one first thing is valley, and to this peak. So in this thing, so transmittance is an increasing order, so refractive index, so automatically it will be so decreases. So that is the change in transmitter. We can tell it is the symbol of del T. That is real note given in the next slide. Is so this is the full future of this third harmonic generation calculation. This is the full part of it. So nonlinear, first we have to calculate for this n2. This is nonlinear refractive index. So intensity dependent refractive index of materials, and this variation of this refractive index as a function of the incident beam radiance are given. So it's given by, so that is n equal to n naught plus n2 I. So this is we discussed previous, right? So n naught is the linear refractive index, and this is the nonlinear refractive index of the fraction, and intensity of this radiance laser beam within the sample. So let us take this one. So del T P minus V. What is the meaning of the del T? So the change in the transmittance. Change in the transmittance is here we calculate. Change in the transmittance is from this point to, so we can from this y-axis this point, the difference between to the T is the change in the transmittance, that is peak value. So first we suppose will be happen, and this is the peak, this is the peak value. So we'll take this del P minus V z equal to 0.406 into 1 minus s power 0.25, the modulus of del phi. So the pi is the change in phase. So first we have to calculate it to the n2 values. So before that we have to apply for the s value. S is the s equal to 1 minus exponential of to RA square divided by WA square. So all of you clear? I think so. It's a square. So S is the linear transmittance. So RA is the radius of the laser at the aperture, and WA is the width of the aperture. L is the effective length. First we have to calculate this S value. So because the radius of laser at aperture, this is you have an given this is a constant that particular laser already given in this instrumentation purpose they given to us. So this value if you are calculated this you can get it this particular thing. So again W is the width of this aperture, that is also the given. So L effect. So L effect is the effective length or to the Rayleigh length. That is also we have a separate formula. So calculated for that is equal to 1 minus exponential of minus alpha L to so divided by alpha. So it is the length of the sample and this is the absorption coefficient. So calculate the L effect value. Okay, so this calculated value you have to use it in this above equation, right? So calculated to this S value, here you have to substitute calculated value, you have to going to substitute in this equation, and then we have to take it over to the del pi in this left hand side. So which will have what will be happen? Del pi equal to modulus of del phi equal to del t peak minus value, that is p minus v, divided by 0.406 into 1 minus s whole power 0.25. So this is now we have to calculate the so del modulus of del phi value. So that particular value you are going to substitute this n2 equal to del phi k I naught L effect. So this I know I have an del phi value calculated the above using to this above equation. So del phi value something is calculated and k is the 2 pi by lambda. So lambda is the wavelength of this laser and I naught is the intensity. So L effect we have to calculate in this using to this given formula. That L effect value equal to sum of the value I can get. So this substituted value we can get for this N2. So this is N2. So substituting this del phi and the S is substituted in the above equation. So finally we can get for the solution of so the refractive index. So what is the conclusion of this particular? So value is the change in the transmittance. If it is the peak value of this crystal of this material, so it will be an so concluded that that is the self defocusing effect. So peak that will be found that get it the out result is the peak value, so that we can set it the self focusing defocusing effect. And to this if it is found this change in transmittance is a valley peak, it shows that self-focusing effect in the closed aperture. So in general, any kind of this compound, if it is one thing is a organic and inorganic compound, one thing is will be happen. One is the self-focusing, so that is valley to peak, or to the self-defocusing, that is peak to valley. So this is one. These two things only will happen. And this is the main picture of this third on this presentation, today's presentation, third harmonic generation. So this is the we have to again we'll see in the next slide. Yes. And next for an open aperture. So above itself this is a closed aperture. The closed aperture calculation we have to discuss. And next is the open aperture. So here we have see that the aperture is remote. The sample will be moved on to this left to right, and then directed, and then recorded the values, and get it from this value we can draw the graph. So the graph explanations will see this So here itself also two kind of the graphs we can get it, right? First one is the, so peak will be the form. So that one we can set it as the, one is the saturation absorption. So this one is the saturation absorption. So reversely we have to formed one peak in that second graph. So that is the reverse saturation absorption. So in this open aperture, so we can calculate for this nonlinear absorption, right? So then this nonlinear absorption, so from this open aperture, one formula is here. So that formula is the beta is equal to square root of 2 into del T by I naught into LFL. So del T is the change in the transmittance. In this y-axis, we can take for this value is the transmitted normalized transistor, right? So transmitted value we have to take it from here and substitute that, and L effect is calculated and the L effect. So this equation is a L effect. Using this equation we can calculate and then substitute in the open aperture. So beta, so nonlinear absorption beta can be calculated using this given formula. So the negative nonlinear absorption has been observed in crystal due to the saturation absorption of material. So if I get for this negative nonlinear absorption, so which mean to the, so due to the saturation graph is the, so denoted as the saturation absorption. Yes. So the coming to this conclusion of this particular third harmonic calculation part. The third order susceptibility psi3 is considered as a complex quantity and it is defined as, this is the formula, it's a single formula. So psi3 equal to, so real of psi3 square plus imaginary of this psi3 square and the whole power 1 by 2. First we have to calculate real of psi3 using to the n2 is calculated in the, this that is the closed aperture, and beta, here beta we have to calculate. So beta is calculated using to the open aperture. So real, and if you calculate the real and imaginary part, again this value you are going to substitute in this part and the square of this value. Again this also calculated and here to substitute and square of this value and then take the root. So we can get for the psi3. Just here I want to show the what I have did by this particular material. I'll show you it. This word file is visible, ma'am?
Yes, ma'am. It is visible, ma'am.
So Ramapriya, ma'am?
Yes, it is visible. Yes, it is visible, ma'am. You can go ahead.
Okay, ma'am. So this is the, so I have a calculator for this material. So this S calculation already given, right? So formula, so in this formula we can get this S value, and to this alpha is the formula is there, right? So alpha value I calculated for my material, and then L effect. So this L effect value, and to this W naught values, input I values, and this is the beta calculated value, and to this delta is change in transmittance value to the speed, and N2 is the value for finally for the calculator refractive index value, and to this imaginary of the psi3, real of the psi3. So these are the two things we have to substitute here, and the square and then the root of this value. So finally for the susceptibility of this psi3 value, here I calculated. This is I had my given for reference. So this is the process of the third harmonic calculation of the refractive index, and that. So where we have to apply for this applications. So optical switching, lot of the applications is there. Here, why should I denote it for this optical switching is just we have to know that. So in the optical switching applications is in this device. So first one we see that this is the let us consider to this input. So do two kind of this output we can get it. Just to see that how can we separate it to this two kind of this output in a different way. So signals of output 1 and 2. So that signals 1 and output 2 and 1 and 2. The signal field is applied to this device. So here it is the particular system setup and applied to this signal field is applied to this device, and this particular signal beam is directed to one or the other of this output port depending on the intensity. So I needed for to separate for this two kind of this way and then different output. So how we have to, what are the what kind of the mechanism we have to insert at this. So see this, here we have given for this input signal field. So both of this signal we have to apply it. Two kind of formula we have to apply. One is this is a known thing, n equal to n naught plus n to I. So another formula is n equal to n2. So first we have to control to this field, we have to apply using to this mechanism, and to this we can get this output that is input signal routed output 1 and 2 depending on its intensity. So using to this particular intensity, the first separate output 1 is we have to separate it in this region. Again to this second mechanism we have to get this second output is the to the output 2. So two kind of this we have to separate it. So using to this particular optical switching in this device. So this kind of this mechanism I have applied in my research paper and as well as published in my thus elsewhere journals. So this is what today, this is I have to get this peak of this particular, that is normalized transmittance, right? So here it is the, what is it, change in the transmittant values and then apply it, and to this we have to calculate beta n2 psi 3, and with this, so real of this psi 3, then what is the second harmonic generation value, and different values where I have to use it for this particular values. So in the case of the, so before that, in the case of this organic and inorganic compound, so in this inorganic one I have one material, so that is an alpha lithium iodide material, I think so. So that is a so reported one. So that the materials will be exhibited to this value of refractive index is the power of -7, and to this absorption value is the power of -3. So this is also on the organic, inorganic, anything will be responded, but the thing is the what is the two things will happen. One is a so saturation of the reversal. So two things will be happen. So what kind of this mechanism we have to use it for it? One here is it the switching applications. So what are the conditions for this optical switching material is, it should be a high ratio of real and imaginary susceptibility. So real and imaginary susceptibility already we calculated. So that will be ratio will be a very high. So the material requirement for all optical switches, so which have to be or the, so WA that is calculated given, right, is a less than greater than 1 and T is a less than 1. These two figures the, but it's defined as the, this using to this formula we can calculate it. So n to the refractive index, alpha is linear absorption for materials, lambda of this wavelengths, beta is the nonlinear absorption. Here response time also very important of this optical switch, very less in time. So what is the absorption time, how they calculated is, so next time we will see that. So this is a response time. So generally in the large nonlinear optical effects, so due to this thermal process of this incident laser power passing through an optical material, the response time tau is associated with the change in temperature. So if the temperature will be changed, the response time also will be changed. The response time for condensed matter has calculated using this particular relation is tau equal to, so rho naught C. Suppose we are using for this optical switching for applications, we need for this response time. So rho naught C is into R square by K. So here is the case of thermal conductivity. This is calculated for this the thermogravimetric analysis, and R is the radius of the laser beam. So using this particular values, we have to calculate it to the tau value. Then what are these values we have to given here? So the standard value is given in the next slide. See that. So this particular standard value you have to taken in this Boyd book, that is the nonlinear optics, is a very standard book. So what are the mechanism is there? So for a particular mechanism, what could the responded to this value of this refractive index and the absorption value. So and what is the response time for this process? The first mechanism is the electronic polarization. So the refractive index is the 10 power minus 6. So in the particular that absorption value, that is psi3, psi3 is the stability. Psi3 is a 10 power minus 22 and the response time is 10 power minus 15. The molecular orientation mechanism, so that refractive index is 10 power minus 14 and the psi3 is 10 power minus 20. And then what is the response time? They see this response time. So 10 power minus 12. So electrorestriction is 10 power minus 4 for the refractive index, and to this psi3 is 10 power minus 16. So the response time is increasing to the 10 power minus 9. And saturated atomic absorption as a, so refractive index is 10 power minus 10 and to this psi3 value is 10 power minus 12. The response time is 10 power minus 8. The thermal effect is C, so N2 is 10 power so minus 6 and to this psi3 is 10 power minus 12. The response time is 10 power minus 3. See here it is a, so here it is a very large value. We are going on to this photorefractive effect is a very large value. So this particular reference data we have to tell it as this which kind of the mechanism we have to use it for this particular purpose. So for if material will be responded to this in power, the value is 10 to N2 value is 10 power minus 16 and the psi is 10 power minus 20 is the electronic polarization mechanism. So that response time is 10 power minus 15. So this is the given data from this Boyd book. This is a very standard book. And this these are the applications. So only one application we have discussed after the switching. So subharmonic generation, optical signal processing, parametric amplification of light, so optical modulator, optical transmission, four-wave mixing, phase conjugation, Raman amplification, spectroscopy imaging, sensor, laser pulse compression, superconducting generation. So in this phase of this application, the nonlinear microscope. So four kind of this microscope we have to use it. One is the first one is the conventional microscope. Second is the fluorescent confocal microscope. Third is the two photon laser scanning fluorescence microscope. Fourth one is the multi-photon microscope. So the conventional is the limiting to this 2D imaging. So next the conventional image is excited by the LED light. So quality is not good. So the conventional microscope quality is not good. So in the case of the second one, the fluorescence for confocal microscope is excited by the laser. In the case of this, see this two photon laser scanning fluorescence microscope. So that is excited by the laser. And multi-photon microscope is it consists of the 3D resolution. So we can get for this 3D resolution is that is will be an that particular microscope is a multi-photon microscope. So that particular 3D resolution based on to the nonlinear optics. So you can see this figure. So this is from this Google figure, optical microscope. And in this nonlinear optical microscope figure, we have to appear at this the optical and nonlinear optical microscope. First one is this way order, and second C is the. So you have to clearly see that. Again, you have to focus on this particular figure. Then we can take this figure as a very linear and focal with this very clear image. So this is the main purpose. And then here it is the two photon fluorescence, that is, and this is the image of the second harmonic generation. I will be in Microsoft, that is fluorescence, optical non-synchrometric, and three photon is the will be appear to this particular image. The third harmonic generation, figure out to this optical heterogeneity, and this This is a coherent anti-stroke common scattering of this particular chemical compound. So there is a just this for our reference. This is from the this is getted from this Google only. This is not done any kind of the things. So is an recently we have to focus on the coronavirus. So that coronavirus is there. Nonlinear optical microscope you can see like that. We can record it to this particular photograph. This is also from the Google. We have to show for this. What is the purpose? What is the usage of this nonlinear optic? So, what is the physical process of causing to this optical limiting effect? So, in this limiting to this nonlinear absorption, nonlinear refraction, and to the scattering. So, this absorption we have to that particular one using to this one limiting. So, we can get this the particular diffraction is will be an we have to converge to this particular phase. This is the physical process. So, what is the optical limiter for this nonlinear optical materials? So, the optical limiter or smart materials is designed to have high transmittance for the low level input while blocking the transmittance for high intensity laser beam. So, just high intensity where we apply for this high intensity laser beam, it will be protect the optical limiter. So, that will be not affected to our eyes. So, we can convert for this low light. So, look up for this smart material, we can use it as a nonlinear optical material. And then, so looking for this end of this presentation. So, this mechanism we have to note both the situation are the same. See this, so it will be not affected using to this particular effect. So it will be controlled to the end to this block to the affect to this avoid the retina. Some of the things are affected, right? Directly we have to giving for this laser light will be affected. So we can avoid for this particular problem using to this effect. And finally, so thank you for your evaluation and to this organizing committee. Thank you once again. So, Ramapriya ma'am.
Thank you, ma'am. Thank you for a very nice presentation. I think there is no queries from participants. I hope everyone would have explored a lot on inorganic compounds with your very nice presentation. And also, it's very good to see a very good feedback from all the audience we could see in the chat box. So, thank you so much, ma'am. Thank you so much for joining us. And also, one more thing here on behalf of Department of Chemistry, we would like to present you an appreciation letter for your wonderful presentation. Kindly accept it, ma'am.
Okay, thank you, ma'am.
Thank you, ma'am. And in this afternoon, we having with us Srimati Sasikala, Assistant Professor of Chemistry, to deliver a vote of thanks. May I request Srimati Sasikala for vote of thanks.
Thank you, ma'am. Thank you, ma'am. Good afternoon, everyone. I am Mrs. M. Sasikala, Assistant Professor, Department of Chemistry, Dr.M.G.R. Educational and Research Institute, Chennai. It is my great honor and privilege to get the opportunity to propose a vote of thanks on behalf of the organizing committee. First of all, I would like to thank our Almighty who gave us tremendous energy and good health to organize this event. My heartfelt gratitude to our Honorable Chancellor, Thiru A.C. Shanmugam Sir, Honorable President, Engineer A.C.S. Arun Kumar Sir, who have given the permission to conduct this event. My special and heartfelt thanks to our today's speaker, Dr.D.Anbuselvi, who delivered a presentation on third harmonic generation of inorganic compounds in a well-explained and interesting manner. Thank you very much, ma'am. I also thank Joint Registrar HNDS, Dean Academic Dr. Arunachalam, Dean Admin Dr. Sendal Kumar, Dean Chemistry Dr. P. Udayakula for their constant encouragement and support in conducting various programs. I also extend my heartfelt thanks to our department head Dr. S. Valliammai, who has keen interest on development and growth of our department. I extend my sincere thanks to all the participants for spending your valuable time and listening us. I would like to thank all the panel members, Dr. Nirmala Krishnan, Dr. Ramapriya, Dr. Durga, Ms. Aparna from the Department of Chemistry, and Mr. Ganesh Babu, System Admin from the Department of CSE, for their contribution to this webinar. I would like to thank once again all the participants for making this event a success. Thank you all.